Stanley, you've got the recording going. All right,
Got
cool.
it.
Whenever you're ready, take it away.
Hi, everyone. Thanks for having me, and thanks for the introduction, Michael. I'm Nathan Lambert. I'm a student at UC Berkeley, and I'm going to be talking about model predictive control in the context of model-based reinforcement learning today. And to start, I kind of want to start with some framing, and that's in novel robotic platforms. So these days, there's a lot of awesome research being done where people are coming up with new ways to make robots and new actuation methods, which open up new applications. And specifically, my intro was through Chris Piester's group, who is making microrobots out of silicon fab and trying to just open up a whole new platform for what robots can do. But when you have these novel robotic platforms, there's a whole new set of challenges, kind of summarized in Grad Student with Tweezers. They're hard to work with. And what you want to do is often demonstrate control for the first time. And when doing so, you might not have a perfect prior on the dynamics of the robot because of things like wires supplying power and other like non-ideal assumptions when designing the robot. And then there's an extreme cost per test when running these. So then we want to design a method for getting controllers that kind of mirrors these challenges. And in this case, it's kind of the method needs to be able to manage some sort of uncertainty. So if we design a controller for the ideal dynamics, we know that the ideal dynamics are likely not true, and then be very sample efficient. So this kind of comes to a problem formulation that I would describe as minimum data controller synthesis for high cost robotic systems. And this is in contrast to a lot of research in RL and robotics where you're trying to very fine tune a certain behavior. But there's another case of generating controllers, which is we just need to generate a controller as fast as possible so this robot can do a simple task like locomotion. So this talk, to cover this, is going to kind of have three sections. First, I'm going to motivate model-based reinforcement learning and talk about kind of why we might want to use models in the first place. And then I'm going to talk about a pretty nuanced theoretical discussion on what is a limitation of model-based RL at this intersection between optimizing a model and a controller jointly. And then kind of at the end, I'm going to move from that into talking about a specific type of dynamics model that might be more useful for model predictive control by predicting the long-term future. So to kind of go back to point one here, it's like why might we want to learn a model and why might we want to use RL? We can think about what robots are good for and what they're not good for. So this is kind of a famous set of examples from 2015 where these robots that are truly remarkable and impressive feats, they encounter a little bit of uncertainty and then the system breaks down. And I think machine learning is a useful tool for studying systems like this where we might be able to use data to understand this uncertainty and therefore control for it. And specifically, my example, I talked about novel robots. I've been working on this robot for pretty much the last 4 years in my PhD. It's called Bionicraft. It uses high voltage to generate ion thrust, and it's completely silent and takes 1 to 3 hours to make one of them. And I can break it within a minute of collecting data. So that's kind of what you can understand when I say we need to do minimum data. I want to fly it once and then have a control policy. On the right is this video where you can see the wires coming off of it. And kind of the crucial question that we haven't gotten past is, how do you know that the wires are not contributing heavily to the flight? And they're a huge part of the dynamics, and it changes with tests. And there's a whole bunch of challenges with the data kind of moving around and being, as I said, uncertain or non-stationary. So then kind of continuing like, okay, machine learning might be useful in this case. And then kind of the motivation of reinforcement learning is also important because reinforcement learning is a very broad framework, which a lot of ML techniques fit into. But as review and kind of how I see it is this framework of an agent interacting with the environment iteratively. And this iterative interaction lets you grow a data set over time. It lets you optimize things in different ways. And it's kind of a general framework where an agent can learn from its environment, even if it doesn't necessarily have a perfect understanding of the environment. And generally, to contrast this from other supervised learning areas, this is just kind of understand my framing and how learning models might help. And In supervised learning, we have this framework of, we have a set of inputs, which could be images. We have a supervised learning system, and it gives us a set of outputs. It can be classes, it can be probabilities, it can be whatever, but in a normal supervised learning system, those outputs directly give us info about the training process. And this training process is then therefore sort of a closed loop, and we have a set data bucket that we're working with, and things don't change, and we can just optimize, 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 and get a better model. In reinforcement learning, this is a little different. So in reinforcement learning in robotics, we often work with states as the input to our system, and we're trying to get an action that the robot should take. But once our system gives us an action, it does not pass back directly and tell us if it did well or not. It goes back through this world that is very hard to model. And then the world has another output, which is the reward of the system, which is actually what we're trying to optimize. So there's this kind of, it's like a open system where the specification is a little different than what is done in a lot of other areas of machine learning with supervised learning. And this kind of leads to a different type of uncertainty. So there's uncertainty in the specification and uncertainty in the optimization. And then what ultimately is the question of like, why would we want to learn a model in this case? And we would want to learn a model in this case so that we can control what is optimized in this broader framework. If we learn a model of states, we can learn to optimize the states with our RL algorithm. So to dive a bit deeper into why we might want to learn a model, I want to review kind of a trade-off that is visited often with like model-based versus model-free methods, especially in the context of reinforcement learning. So you can see on this slide, I have model-based methods and I include model-based RL, and then there's also system identification, things like PID tuning, which can use model heuristics to do them. And then there's model-free reinforcement learning. Kind of, it's just model-free RL because there isn't like model-free classical control. That's kind of magic and doesn't really work. But there's some important trade-offs here in what models give us and what omitting models might help with. So specifically, like model-based methods are useful for, you can use the model offline. There's an idea that we might be able to generalize, they're sample efficient, but if you've ever tried to work with model-based RL, working with the code is hard. It's hard to get set up, and it kind of requires a lot of computation to actually compute the actions that we want to do. Where model-free RL can kind of have different properties. But if we go back to my original motivation, the biggest decider for me was kind of the sample efficiency, and then I've kind of grown into the area to see some of these other benefits. So to go into the model-based RL literature a little deeper, these are kind of things that people are using the models for. And I start with data efficiency, and this can also be used in, a lot of ways. So the kind of dashed lines are imagining that you can use a learned model as a simulator. So you can like generate new data when you have your basic model of your robot. But then like once you have this model, there's a lot of things that people are trying to use it for. So there's other recent work from model-based RL where they're trying to generalize across robot classes, which is in the case of like, if a leg length changes, if the mass of your cart and cart pull changes, you should be able to parameterize your model correctly to generalize across these systems. And then one that I think is coming soon with kind of the interest of kind of beneficial AI and making sure AI isn't harmful is a set source of interpretability. So if you have a model, you can understand how your system sees the world and understand what it's optimizing over. And therefore, hopefully we can try to tease at why is a specific action chosen given the information that the system has. When you compare this to model-free RL is a black box neural network that gives you an action depending on a state. And it might not be smooth, it's hard to tease at. So this is kind of like a motivation for a lot of the different reasons why you might want to use models. In my case, I got into it from a specific robotics problem, but I think it's a very elegant tool that we can leverage as we're collecting a lot of data about our specific environments. And there's one last fun reason why we might want to use models. If you're very like bottom-up motivated or studying the brain, a current opinion in neuroscience, it might not last in the field, is hard to track, is that if you give a set of mice a task, how they determine their actions is by like replaying visual information through a maze or through a task, rather than just kind of instantaneously knowing the action that'll help them get to rewards that rewards that they remember. So I think these biological motivations are very interesting, but they change very fast. So if you need to make a strong argument, I would go off the previous slide, which is things that people are already doing rather than studying biology, which I'm not an expert in. So if we kind of combine this system specification discussion of reinforcement learning with the idea of using models, we converge at this system of model-based reinforcement learning. So I'll go into these components to kind of review how they are done in various papers just briefly after I go over the slides. So we have like a dynamics model, and then we have some set of control and planning and a feedback loop. So while an agent is improving, the agent acts in the environment. This gives us your state and your reward. And then you learn some model of the dynamics. And when you're learning the model of the dynamics, it can be parameterized in different ways. This equation is showing you're maximizing the log likelihood over the probability of transitions from a given state. So this is a probabilistic model of the dynamics, but there's other ways that it is done. And then finally, with the dynamics model that is learned from data, the agent then uses the model to learn to act in the environment. There's multiple ways to do it. The way that I'll be discussing is the most popular to date, which is with model predictive control, which is kind of like unrolling the dynamics model and then choosing the best action. So the first component is this feedforward dynamics model. And generally, it's important to consider the problem setup that reinforcement learning and model-based RL works in, and that's in a Markov decision process. So if you have a simple trajectory from green to red here, you discretize it, you take samples, and then you learn to predict the change in between each sample. And mathematically, what you see is that you learn to predict the state at the next time, given the current state plus some learned residual that is from the current state in the action. It's been really useful for a lot of different situations, and happy to point people to more work after the talk if they're interested. But it really just comes down to training a feed-forward neural network to take in states and actions and predict the next state of some sort. And this supervised learning problem is very, very simple. It's just a small neural network, and you train the data, and it has reasonably accurate predictions. And this prediction mechanism on the left is often called one-step prediction, which is something that I'll revisit later in the talk. So the question is, if we have one-step transitions, it's how do we then predict trajectories? Trajectories tell us the long-term behavior of our system. And if you've studied like optimal control and other techniques, the long-term behavior is what we're interested in when optimizing actions very frequently. So if we have this one-step prediction, we end up creating trajectories by a compounding prediction. So we pass, if we want to get something like this visualization where we have different trajectories of a given state, we pass this function output back into itself. So we do this for each time step. We pass this in like 3, 4, and then all the way up into how far we want to go. And it turns into many compounded neural network passes. In practice, when you do this, neural networks have very weird behavior where if you pass them into themselves a lot, you have these compounding errors. So if you want to predict further into the future with these one-step models, what people end up seeing is that it's actually harder to predict accurately far into the future. So then kind of, I'm adding some uncertainty into this prediction mechanism, but what people do is they use this in model predictive control. And model predictive control is an optimization technique where you predict trajectories in your environment. There's plenty of work that does this with true analytical models and with learned models. So you predict these trajectories into the future, and then you choose the action that gives you the best predicted reward. And what this looks like in a sample-based system, which is what most of model-based RL uses, is you sample actions from some distribution. You plan to a certain horizon H, often between 20 and 30 steps into the future, which can be much shorter than the task at hand. And then you kind of like, this actual planning step is computationally intensive because what happens is you predict all of the states time equals 1, and then time equals 2, and time equals 3. So you have to have essentially a long for loop where you're passing this neural network into itself, which is hard to get running in real time. So one of the examples of what I did in model-based RL a few years ago was using this kind of vanilla setup that I've covered with one-step dynamics models, and we predict trajectories, and then we choose the best trajectory to compute the best action. So we put this onto a quadcopter, which is a crazy fly, and kind of crashed this a bunch of times and trained a model, and eventually it got to the point where it could fly, but it's very subject to drift. So what I mean by that is it only has local state variables, and it was applying PWM voltages to the motors directly. So we had no control over the XY position really. So essentially, I think it is in this flight, you see it's controlling its attitude, but then it just drifts into a wall. So I kind of needed to get a bigger room, but this is a exciting result because I didn't change much in the framework. I had to write some code to make this work fast on a GPU. So our model predictive control only ran at 20 to 50 hertz, which is pretty low compared to the internal controllers of a crazy fly, which is like the PID controllers generally run upwards of 500 hertz. But the planning capabilities of just a feed-forward model and sampling-based control were able to fly this robot. So that's kind of where I started in the area. And the idea was that this robot was similar to the Bionicraft that I showed earlier.
Can I ask a question?
Yeah.
So your sampling trajectories on like from the current policy, is it, how are you sampling trajectories? And
so we kind of randomly sample actions of like 500 random actions, and then the sequences are of length h of the horizon, and then you plug in that random action sequences model.
okay, so when you're learning the model, you're not following a policy to sample actions. You're just randomly.
Yeah, there's like the 0th iteration is a random collection of actions.
Okay, thanks.
Yeah, that's a good question. How to actually parameterize that distribution is probably the most exploited area of research in model-based RL right now. Most of the recent state-of-the-art performances have been by changing the distribution of actions that you sample over in order to get better model predictive control performance. So given this kind of starting point of model-based RL, there's a lot of limitations in this approach that just uses a feed-forward model, sampling-based control, and actually a robot in the real world. And we're not really optimizing the model for control. We're just optimizing a model to fit whatever data we have and not really thinking about, is a certain model better for control, or is it just better for modeling the data that we have? And that's kind of a distribution mismatch. And then given noise of real systems, modeling accuracy is limited. And as we were talking about with the control, we sample a bunch of random action sequences. And when you have a higher dimensional controller, your sampling is going to be very sparse. So it's stochastic and you're not going to get the optimal actions. And then practically things that I ran into are computational limits. The most interesting software I wrote for this project I just showed was, how do you get CUDA code to run at 50 hertz when you're essentially passing feed-forward neural networks at, like, you have to do hundreds and thousands of forward passes in this little while loop, and then you send the control to the robot, and that sucks. We don't want people to have to use a GPU. And just getting useful data, I was running around catching this robot. It would figure out that going really fast, it would hit the ceiling and I would catch it, which is not safe and something else that we need to work on in model-based RL. But I'm only going to talk about some of these in the talk, and kind of this first point is going to be me talking about pairing the model and controller optimization. So the controller optimization is separate from the model, and we think that they should be together. And I'm going to go and talk about why that is the case. So generally, there's one key assumption when you're optimizing a dynamics model for control, and that is that if you maximize the log likelihood, if you maximize the accuracy, then you're going to get a higher episode reward. Then you're going to perform better. And our question is, to what extent is this true? is an accurate model always a useful model? So to take a step back, we can look at kind of the origins of model learning for control. And that is on one hand with system identification. In system identification, people set up elicitation trajectories is the word that's used, where you hand design trajectories to cover your whole state space in hopes that your model is close to the analytical truth and covers the whole like global tasks or set of tasks. And then you use that model to learn control. In reinforcement learning, which is kind of like this iterative unstructured method that I introduced at the beginning, the data distribution that you get is very different, but the assumptions that people have on their models is very similar. So people might assume their model acts like a system identification model, but in reality, we observe a task-specific subset of the data and it's iteratively learning. So our distribution slowly shifts over time. And what we get is kind of, if we have a task, you have this best trajectory and you kind of learn in an area around it. And it's very different than what people might have assumed is originally happening with their model. So kind of with this introduction, I'm going to revisit the model-based RL framework. I'm going to visualize this loop in a slightly different way and point out where new connections will need to be made. So in a loop, the loop will be connected. You kind of have this policy, which is the agent. The agent interacts with the environment, and the environment gives us a set of data. The set of data comes from these trajectories, which is incorporated of state trajectories, straight transitions, and reward. And then with these trajectories, we train a dynamics model with maximum likelihood. Blue here is just train an accurate model. And then normally this model is then used for the policy here. There's no real direct links between control, and what we propose is kind of there's an objective mismatch where the reward should be used in optimization of the dynamics model and or the policy. And there's a numeric way to visualize the shortcoming here. And this is a dual optimization in model-based RL where we do one of these optimizations at either time. We're doing one and then the other. It's one optimization and then the other. And if you've ever tried to do a multi-objective optimization, there's no guarantees that by optimizing a totally different function, the one that we want is going to get better. So this difference between the training and the test time for model-based RL is what we call objective mismatch. And it's kind of what we're going back to see. What we want to see is that whether or not this assumption of model learning with maximize accuracy doesn't maximize performance, we want to see if this is true. So kind of in the next set of slides, I'm going to visualize what the assumptions are and then what the data is to look at this correlation and see whether or not it's true in model-based RL. So if we wanted to visualize the ideal relationship, there's two variables here. We can put them on a plot. We're going to see something like model accuracy on the bottom, where a model is more accurate if you go to the right. And then using model predictive control with the learned model, we're going to have episode reward on the y-axis, where it's ultimately saying, if the model gets better, we might expect a relationship like this. If a relationship is like this, you as an engineer, it's really easy to use. You just we all do our supervised learning hacks. We get the accuracy really good. And then we're like, great, we're ready to go run this on the robot. But in reality, that might not be the case. And there's actually another question that we need to ask that kind of goes back to the model learning origins. And it is, on which data sets is this most important? So there's kind of three data sets that we can think of when we're doing a robotic task, if we're using classical controllers, and then also what's happening in a reinforcement learning loop. So these kind of are an expert trajectory. If someone knew how to solve the task perfectly, they could do this with the expert trajectory. That's one set of data. And then there's on policy data in a reinforcement learning loop, which is kind of like this iterative growth of a data set. And then there's global data. The global data is these elicitation trajectories that are trying to cover the whole space. So in reality, these data sets look very different. And what might have been the case in the past is that someone with a learned model would expect it to be uniformly good across all of these different data sets. But there's also like, which one is most important? If you just want to solve one task with robustness, I think kind of in between expert and on-policy data is the most important, but there's a certain elegance to the global data that could help you. So what we did is we collected a ton of data on this half cheetah task. So half cheetah kind of is this awkward running animated creature that for some reason a lot of RL researchers work on a lot, and it's pretty weird, but we collected a bunch of different dynamics models. And then with these curated data sets from the last slide, we looked at how accurate the dynamics models were and what reward they got on the task. So you can see that in the expert and the global data sets, there's almost no correlation between what the model accuracy is. So the x-axis here, as you get more accurate on this leftmost set, the reward is pretty much uncorrelated, and same with the global scenario. So the dynamics model that we're learning in model-based RL is very specific to what we are doing, which is this on-policy data. And even when looking at the exact data that the model was trained on, it's only a weak correlation. So the way that I see this is if you take a sample of a certain model accuracy, so if you look at 2 here, you can then sample a model from that accuracy, and you could get a model that gives you reward of 2,000 or reward of 6,000. And all of these data points are averaged across multiple random seeds for the environment, so that we're getting at the accuracy, we're getting at the performance of the model rather than just the performance of the initial state. So this is really goes to ask the question of what should we be optimizing, and what is our optimization of dynamics model accuracy actually doing? And we took this a step further, and this is a really cool experiment that on a different task. So we ran on this cart pull task, we ran an adversarial attack where we were trying to get a model that is very accurate, but gets low reward on the task. So this is kind of broadly using the word accurate, and it goes to show that people, like, the word is kind of overloaded, where an accurate model is in one sense accurate, but we don't necessarily know what that means. So we took the CMA ES optimizer, the Python package, don't really have to change much, and we wanted to optimize the weights and biases of the output layer of the network. And what we did is we wanted to get a high accuracy, so maintain a certain log likelihood while reward. In just a few trials, the optimizer was able to decrease the reward by like 50% on the original performance of the dynamics model just by fine-tuning these parameters. And the intuition of this is very important. And it's kind of, it can be easy to say like, oh, like, why are we optimizing models at all? Like, what is actually happening here? And what's happening is if we have kind of an overall accuracy of the model, we're fine-tuning the accuracy on the specific task down, but the rest of the accuracy gets slightly better, so that on average, the model accuracy remains the same. But if we are training the model by hand on our whole data set, there's no tools right now in supervised learning that I or you could use to understand which part of the state space your model is accurate on. So model-based RL practitioners are kind of going off this one number in order to see how their system's performance is going to be. But in reality, it's much more complicated than that. So here, there's a couple of methods to mitigate what we call objective mismatch, and I'll end up going into one of them in more detail. And one of the things you can do is to train a model to predict trajectories. So if our idea is that our controller is predicting trajectories, therefore our controller is optimizing trajectories, therefore our model should be predicting trajectories. If you're doing supervised learning, there's this thing called the batch. Normally your batch is randomly sampled. And what we did in this left experiment is instead of random samples, you pass in a batch that is an entire trajectory at once. So all the gradient updates are pointing in the direction of an accurate trajectory rather than a random distribution. And the correlation becomes a little bit flatter. So if you're at a given accuracy, it's a little bit easier to know that your reward is going to be higher. This is not a full solution. The solution that I'm going to go more in depth to is in a few slides. And it's kind of saying this is a hard problem. And another thing that we did is we know that our data distribution is going to have areas that aren't important. If we kind of gently reweight our model training to be around an expert trajectory, that is to say, when you update the actual loss in your neural network, there's kind of a weight that goes to say, how close is this batch of data to the expert data? The performance is actually much more sample efficient, and you can you need less data from your environment to actually solve a task when you're kind of reweighting around a task of interest. So what objective mismatch is really saying is the metrics we're using to determine model accuracy are kind of too loose to really guarantee any performance improvements, and we need to understand this mechanism a bit more and spend more time designing the one-step predictions in model-based RL. So the next step, and it's going to be the third part of this talk, is kind of from these one-step dynamics models where we're predicting a change of state, what if we can design a model that predicts trajectories? And that might be more useful for this model predictive control framework that we've been using a lot. So far I've kind of covered why I think model-based RL is useful, and then this objective mismatch section of the talk where it's kind of illuminating that model-based RL is pretty complicated in these handoffs between different learning systems. And now I'm going to go into a section talking about a dynamics model specifically optimized for predicting trajectories and what it's good for, and then finally kind of saying what's next in model-based RL. So onto this model for predicting trajectories. And to start, what might this look like? And the crucial starting point when you're designing the systems is where are we working in? We're working in this Markov decision process where we have discrete steps based on states and actions. And on the left is the standard one-step look ahead where you're predicting a change in state, often called like a delta formulation. And on the right is this new work that we proposed, which is on a trajectory-based model. And what it's useful for is ultimately by weaving in direct time dependence and control parameters, we're trying to understand the long-term behavior of the system. And the next slide, I'm going to go into more detail about how we actually train this with supervised learning and then what benefits we get from it. So this trajectory-based dynamics model that I will go into is kind of control conditioned. So if you see, when you see theta pi here, that's something like PID control, LQR control. So we tested this on a variety of tasks, some of which use PID and some of which use LQR. And we kind of changed the values of those parameters. And then based on the change of the control parameters, we're trying to predict the long-term future. So what happens is in order to predict each steps into the future, there's the starting state at time t. So you can see like on the screen, the first set of arrows comes from time equals 0. The second set of arrows comes time equal 1. And then there'd quickly be too many arrows for the figure to be legible, but you can think the same thing from further into the future. And then there's the prediction horizon, which is how many steps into the future you want to predict. And then these control parameters. And what we've shown numerically is that there's a set of advantages, and they are that there's better long-term prediction accuracy. So our fundamental hypothesis of can we predict the long-term future turns out to be true in this. And then by labeling the sub-trajectories, you get more data for your supervised learning problem. And I'll show how this different labeling can lead to computationally efficient planning when you're actually implementing this on a real-time controller. And then there ends up being stable uncertainty propagation. This is mostly through avoiding compounding error. And this is the only one that I don't have a slide for in this talk. It's kind of a nuanced discussion of what happens when you're doing these one-step models and how does the error propagate. And you might have seen this on the slide, this kind of tuple. And this is kind of just the supervised learning samples, which connects to the data collection rate proportional to L squared, where L is the length of your trajectory. So I'm going to go into the benefits of this model here. And the first point is kind of comparing the cumulative prediction error across a trajectory with other potential models of interest. So here in red is the new model, and we also compare it to various types of one-step models where there's the D deterministic model is a mean squared error predictor, and PE is a ensemble of log likelihood maximizing models. And then the last one we compared to was a recurrent model of LSTM. And the first three tasks are simulated robotic tasks where Cartpole is using LQR, and then Reacher and Quadrotor were trained on PID controller data. And finally, we had some crazy fly data, which we also showed the prediction accuracy for this type of model on a real data set was more accurate. And kind of we're just interested in this long-term behavior if the model is more accurate. And this is kind of like the starting point for the work was like, okay, this seems to be reasonable. And then we're starting to think about how we can use this, and this using it is more of a direction of current work. So I mentioned the efficient planning, and this happens by collecting more. Well, first off, there's more labeled data. And here's kind of the idea for how you get more supervised learning data is if you sum over all of the sub-trajectories. So you start at all the time indices and the trajectory is length L, you end up getting a growth in the length squared, which realistically, if you're practically using these things, is way more data than you would want. Because if you have trajectories of 500 points, that is so much data very rapidly. But then you can predict the future with a time index. So if we take a step back and look at the one-step prediction, what happens is each step in this MDP is a forward pass of the model. So in order to predict at time equals 10, you have to do 10 forward passes of the model sequentially. So you can't leverage the parallel nature of a lot of deep learning architectures. But with the trajectory-based model, we have this H input here. And with parallelizing this input H, we can kind of pass in all the times we want to predict to at once. So you pass in a vector of H's and it gives you a vector of predictions out. So you therefore don't need to do a serial planning loop where you're planning one at a time. You can just plan everything all at once by passing in a big matrix to the model. And this has a lot of conceptual benefits, and actually going to use this in control is something that we're working on right now. So
I have one question, if I can jump in for a second. Could you say again what the theta pi parameterization of that is? Does it include like a goal in addition to a PID control? Or is it just like hover? Okay.
It can. So depending on the task, like the cartpole task, we always had the goal be going to 0, 0. But with the Reacher task, we had different positions in the 3D state space for like where your arm wants to go. And then the PID can encode that by having different target joint angles. So a joint angle of versus like 60 or 30 gives a much different parameterization of the arm. So, and this, I'll talk a little bit more about that parameter later on, but that's one of the big limitations of the work is needing that parameter. Oops, skipped one. So one of the cool things, just this going into the supervised learning part is like, how does this more labeled data turn into a useful RL tool? So kind of this heat map is showing with versus a deterministic one-step model on the left and the trajectory-based model on the right is the mean prediction error given a certain state, and then like how long the trajectory is and how many training trajectories you have. So darker here is better. And generally the trajectory-based model, if you look at it as a whole, is much darker. It's doing better, but something that is generally useful for anyone that's thinking about RL is like, how does this evolve over time? So if you take slices of this heat map, say this is a specific trajectory length. So that could be like the length of an episode in your trial. And here in like about 75, if you take a slice here, it turns into like a learning curve over a number of trials. So it's kind of saying, how quickly does your model become accurate? And if you visualize what's going on in these slices is the trajectory-based model starts off more accurate by just the parameterization, looking at the long-term future, and then it quickly converges to a higher accuracy. So it's just a different behavior from a different supervised learning approach. And what we are hoping to do is to use this in model predictive control, where in standard model predictive control, you maximize over the inputs directly, you're maximizing over the input space, and then you're propagating the predictions through a learned model. But that behaves a little bit differently in the trajectory-based model, where what we now need to do is optimize over these control parameters while predicting into the full future with this different model structure. And then you have to compute the action from your control parameter. So if you actually go, when implementing this with something like PID, it's somewhat tricky because you have to go in and then run your planning as if you are changing the PID parameter at each step as you plan into the future. You can't just like create a new controller easily, where that's something that actions have that is nice from them. It's a little bit easier in an MDP to just like throw a new action at it and see what happens. Planning over the control sequence takes a bit more of a nuanced actual implementation when you're trying to use this. And this is like, I'm deliberately highlighting the challenges of this, because if you just look at the data I showed, it could be like, okay, like why isn't everyone using this? And I kind of summarize this as like a no free lunch when you're doing dynamics modeling or when you're doing any bit of learning. So what happens is there's always a trade-off in your model. Your model assumes certain things. And it's kind of like in RL, where in RL we are controlling certain things and then we're optimizing over what we are controlled for. But there are things that we are not controlling over, and that is challenging. So in the case of the trajectory-based model, we get long-term prediction accuracy, but we need some controller parameterization. So we've been working for over a semester with trying to do some more machine learning to get this to work with like neural network policies. But it turns out that the like neural network policies, the space of them is too weirdly formed that it's hard to make predictions with them, even if you shrink them down a lot. And it's kind of like this model works in one case because it's very well structured for what we're doing. And hopefully that works for model predictive control. But in general, it's not globally better. So your data is limited, and what you can extract from it is you want to extract from it what you're going to use. And like one-step models are broadly applicable, and it's kind of extracting the most general information from your data to see what you can use for it. So it's kind of going to say like, there's a bit more, if you spend a bit more time developing what your model is doing in model-based RL, hopefully there's a lot of benefits. So I'm just have a couple slides left, but to recap kind of what's happening in model-based RL and what people should be working on, there's these theoretical contributions, and the last one I'll show an example of in a future work slide, but it's kind of like this structure and this system works when it's set up, and people have seen some cool results with it, but some of the actual like linking between the systems people have made needs more investigation. And then practically, we need to make this so it works on more types of robots, so that's a bit safer. And these practical considerations can also be linked to all of RL. Like getting safe samples of data is very important and currently underexploited because a lot of work is in simulation. But what I'm currently working on is trying to reduce the computation of model predictive control. So we're trying to see if we can do some sort of imitation learning to reduce to kind of imitate the big action distribution that we sample over. And then if we do that computation offline, and then online, hopefully we can learn a feed-forward policy or some other parameterization to run the controller much faster. And the biggest face level reason why this is hard is sampling-based control is really uncertain. So kind of an illuminating plot, even on a simple task here like cart pull, if you fix the state of the cart pull and then you rerun sampling-based control a bunch of times at that state, there is a very wide distribution of actions over which the MPC returns. And what people kind of think, so in the side rooms of the conferences, people think that model-based RL with MPC works by averaging out to the best sample over time, which is interesting and just goes to show how suboptimal its kind of thinking is right now. But we need to manage this uncertainty if we want to do any sort of imitation learning on it. It's just too hard of a learning problem to start with. But the potential of this work is very high because then you don't need a computer with the GPU. Most small processors can run a neural network policy at upwards of 1 kilohertz, and that's way easier to work with. So to kind of loop back to why we might want to use learning for robotics, why we might want to learn models, and why reinforcement learning, it's that like we're working in this world and we know that there's uncertainty in the world and there's not enough data to model it perfectly, but we might be able to model part of the data and then get something useful out of it. And RL allows one to build structures to optimize for what matters. So ultimately, if you dig further into what RL is doing, it's optimizing over what you give it. And if you have a very complicated world and you can learn a simple model in the area of interest, then RL might be really useful for optimizing what exactly you want to do. So it's kind of in this problem formulation that RL can be very useful. I wanted to thank collaborators. So these are my co-advising structure here with Chris and Roberto, and then a bunch of collaborators by which this work has represented contributions from. And I'm going to stop there. So thanks for having me, and I'm happy to answer any questions now.
Great, thank you for the great talk. It was a lot of, I feel like I'm gonna have to watch this again. It was a lot of really cool information, but it's also like challenging that basic assumption is very interesting. So my roommate is backing me right now. If anyone has any questions, just unmute or ask in the chat.
Oh yeah, I see there's one little chat. Oh yeah, it was a chat message. I didn't miss any questions in chat during it. I've definitely done that when lecturing.
I guess I have one more question just to throw in. Is there a sense from your talks in the communities about like what is the thought process toward? It seems like a lot of your work, and maybe I'm mischaracterizing, is focused on good data sampling. So like we have this hard problem to model. We want to make sure we're sampling in the right places so we're getting a good model there. How do people think about like the other side of that problem for like regularization of the model? Saying like we have few samples, so let's like reduce the complexity of our neural network or reduce like how much we can model.
Yeah, so there's one work that I think is great, which is like they realized the task was simple enough and they downgraded from a neural network to a linear policy, which is just like a matrix representation, and it still worked. I don't see that much regularization. It might just be because the model is so like we use 2 layers of like 128 neurons as like the default. So it's such a small model that there's not much downgrading to be done. And that's kind of what everyone has just been using, to my knowledge, with a little bit of like linear policies, which I'm happy to see people not just always using neural networks. And Gaussian processes are popular, but it's kind of hard to do online stuff with Gaussian processes.
Well, thank you.
Yeah.
All right, if there are no more questions, let's thank Nathan again, and thank you everyone for joining today.
Thanks for having me.
We can send you a link to the recording once it's done processing and it's uploaded.
Yeah, that'd be great. Thanks for having me. Happy to
Thank you
answer.
so much for coming in, and even though it would have been nice for you to come back in person,
Yeah, it would have been fun. Maybe eventually. Things seem to be getting better. At least in California, like California opened up vaccines to grad students for whatever bizarre reason. They thought they were educators.
All grad students, or
pretty much. It's
wow,
ridiculous.
Here it's rolling out to the TAs. Like
yeah.
Some of my friends have gotten vaccinated already. But,
yeah, I think people who are actually